Welcome to Math 31, an introduction to calculus. We are in chapter 5, looking at curve sketching. Lesson 5 today. We've already done some curve sketching, but in this lesson we will put a whole bunch of different ideas together in terms of how do we get the most accurate curve. But first we have warm-up, and I expect that you did this warm-up in class. So I will just display answers here for a few seconds. If you haven't done them, then you can pause, do the questions, check the answers. But I will display these for a few seconds before I move on to the first example or some explanations. Here's warm-up question number 1. And warm-up question number 2. We end up with this graph. All right, on to some notes looking at even and odd functions. All right, when it comes to sketching the graph of a function, the first step will be to find the intercepts, which we've already looked at. To find x-intercepts, we said y equal to 0, and we solve for x. And as we've also demonstrated, if this turns out to be a fair bit of work, we are just going to skip this because it's not really a calculus topic, but it will help us get a better graph. We want to focus in on the calculus topics. And then to find the y-intercept, just plug in 0 for x and evaluate. Next, we'll look at the symmetry. So sometimes we can do this. We can sketch a graph without symmetry, but symmetry can increase our efficiency if we have a function that's symmetric. So two types of symmetry that we're going to talk about. First of all are what we call even functions. Now notice this is not an even degree polynomial. This is something completely different. An even function is defined by this first bullet. If I can replace the x's in my function and the result is exactly the same as if I don't have a negative x, then we call it an even function. In other words, it's symmetric about the y-axis. So here we have an example of an even function. And so here's one point that we're looking at, that if I plug in -3 into my function, the result that I get, the y value, is exactly the same as the y value for f of +3. And if that's true for every single point on the graph, it means that on the left side of the y-axis and the right side of the y-axis, they're mirror images of each other. And we call this an even function. So if that's the situation that we have, then when it comes to sketching a graph, we can just collect all the details about, let's say, the positive x values, and then just mirror them for the negative x values. An odd function is a function where if I replace the x's with a negative x, I get the negative of the original y values. And we say this is symmetric about the origin. So this is a rotational symmetry. An even function is line symmetry, so there's symmetry across this vertical line of the y-axis. Here we would say this is rotational or point symmetry. There's symmetry about the point, which is at 0, 0 at the origin. So for example, if I was to take an x value of -2, calculate the y, I would get exactly the opposite as if I put in a +2 and evaluated the function. In other words, this distance here to this function value and this distance here to that function value, those two distances are exactly the same. And here's how we can visualize the rotational symmetry. This won't be perfect, but it'll give you the idea. So if I was to take my original curve here and rotate it about the origin, and you'll see as I rotate it kind of shifts off slightly, unfortunately. But essentially what we end up with is exactly the same shape as we originally had on our original function. Okay, so that's rotational symmetry. the f of negative x is equal to negative f of x. So here's how we test for it. We want to classify each of these functions as even, odd, or neither. And as you can imagine, here, even function, odd function, you've seen functions that are neither of these. So most functions won't have a symmetry, but some do. So what we do is we take our function and we replace the x's with negative x. And then we simplify the expression to see, do we end up with exactly the same as we initially had, or, as in this case, once I simplify, because my exponents are both odd, that negative can come out. I can factor it out as a negative, so I get the negative of f of x, which means this is an odd function. We'll do the same process for question number 4. We'll replace all the x's with negative x. Not nearly so pretty, but it gets the job done. And because all my x's are squared, it turns out, oh, what I end up with looks exactly the same as my original function. In other words, this negative, remember from Math 30-1, is doing a reflection in the y-axis. And this reflection in the y-axis looks exactly like the original function. So in this case, we have an even function. Why don't you pause the video at this point and do questions 5 and 6, go through that same test, determine is each of these even, odd, or neither. Well, for question number 5, hopefully you recognized it's an odd function. And you can see my process there. I'm able to factor out a common factor from the numerator of -1. And so I get the negative of the original function. For number 6, this time I get neither. So in the numerator, I am getting that common factor of -1 I can take out. The denominator now also has a common factor of -1 I can take out. Those negatives cancel out. But now notice my denominator is an x cubed plus 1, not an x cubed minus 1. It's not identical to the original function, nor is it the negative of the original function. So we say this function is neither even nor odd. Let's look at 2 examples where we go through the entire process in order to sketch some curves. Question number 7, and you see on the right side that multi-step process that we will go through. So first of all, we want to look at what would the domain for this function be. Well, we can see that there's a variable in the denominator, so x cannot equal 0. There's my domain. This also means that there is no y-intercept. But if I make my function equal to 0, I discover that that will be true when my x value is 1. So I didn't show the process. You've done things like that in the past. You can do the process just to verify that you have an x-intercept at 1, 0. Then we check the symmetry. When I replace the x's with negative x, well, in the denominator, that x squared will again be an x squared once I square to get rid of that negative. But in the numerator, I'll have a negative x minus 1. I can't do anything to that to make it look like x minus 1 all squared. So this is neither even nor odd. So I need to check both sides of the y-axis, positive x values and negative x values, and find the details all the way through. Well, let's think about asymptotes. Horizontal asymptote, as x approaches infinity, we have this function, and I didn't show the details, but you'll remember our process was to multiply the numerator and denominator by 1 over x squared. And when we do that, we're left with this first term will turn into a 1. This will be a minus 2 over x, and this will be a plus 1 over x squared. Both of those go to 0, and our denominator will be a 1. So we get 1 over 1, y equals 1. There's my horizontal asymptote. Looking for a vertical asymptote. Well, we had that non-permissible value where x was 0. And so I do a left-hand limit. And because my numerator and denominator are both being squared, they can never be negative, which means even though my denominator goes to 0, in both of these situations, so my limit is infinite, it'll be positive infinity from the left side and also from the right side. So there we have the vertical asymptote. The next stage is to look for critical points. So what I did was I expanded my numerator so I wouldn't have to use the chain rule, and actually I divided each term by x squared, so I rewrote it as powers of x. That simplified it, so I didn't need to use the quotient rule either. Well, that makes things a little bit easier for this question when it comes to taking the first derivative. Here I have the first derivative, set it equal to 0. I use that strategy from the beginning of the semester where I'm factoring out the term with the lowest exponent, so the negative 3, and that gives me an x minus 1 factor here. This x to the negative 3 is an x in the denominator, all cubed. That can't make the function 0. Only this x minus 1 can make it 0, so I have one critical point. On to inflection points. So I look at the second derivative here. And since I have the first derivative, I take the second derivative. This time I can factor out a common factor of negative 2x to the negative 4th, leaving me 2x minus 3 in the brackets. When is that equal to 0? Only when this 2x minus 3 is equal to 0. So I have one inflection point as well. Well, that gives us lots of information, and it helps us set up our number line where we have x being 0, that's my vertical asymptote. When x is 1, that's my critical point. And when x is 3/2, that's my possible inflection point. So as I think about my first derivative, right away I did the first derivative test in each interval around this critical point. So notice I didn't have to do anything in between here because everything to the right of this critical point where x is 1, it'll be, in this case, increasing everywhere over that interval. And then the second derivative. And so here with the second derivative, you can see my test point was x being negative 1. First derivative was positive, second derivative positive, so I know it's concave up. Here I use this critical point where x is positive 1. My second derivative test said this is concave up, so that means I have a relative minimum at the point 1, 0. It's concave down to the right of 3/2, so that means I do have an inflection point where x is 3/2. And now we can plot some points. So I can draw my vertical asymptote at x equals 0, plot the point 1, 0, and that'll be a relative minimum, and plot the point 3/2, 1/9, and that's where I'll have an inflection point. So my concavity will switch from curving up to curving down at that point. Here's what it will look like. Vertical asymptote at x equals 0, horizontal asymptote at y equals 1, and I have my relative minimum here and my inflection point there. I know that my graph is increasing in this section. I know that from both sides, let's just look here, yeah, from both sides of my vertical asymptote, I'm approaching positive infinity. So I know my graph is going up on the left and up on the right. Here it'll be concave up. Here it'll be concave up all the way to this inflection point. So this is what we'll end up with for a rough look at our graph. More or less like that. My minimum isn't quite in the right place, but you can do a better job than me at this point. So hopefully you end up with a curve like that, concave up, concave up, concave down from here. And again, I will pick up your page and look at it on edge to see if that concavity changes exactly at this point when we're in person. All right, that is it for this question. Let's look at one more example. And why don't you pause the video, try this one out. This will take some time, not quite so simple to get the first and second derivatives for this function. So pause the video, work through that set of steps that we had here from A through J. And for this one, you will find, I think that it's an even function. So once we get down to putting information on a number line, you don't have to do both sides of the number line. You can do just the positive values for x. So that's a tip as you get into question number 8. Pause the video here, restart it once you're ready for my input. This function has no non-permissible values, so x can be any real number. It's defined for all values from negative infinity to positive infinity. And 0, 0 is the one intercept that we have. And because our domain is all real numbers, there's no vertical asymptote. There is, however, a horizontal asymptote. As x approaches infinity, we find a horizontal asymptote of y equals 0. Here's what I mentioned earlier, that when we do that test replacing all the x's with negative x, we end up getting exactly the same expression as our original function, so we know that we have an even function. Next, we will take the derivative. So here are the details of my derivative. Low d high minus high d low required the chain rule. I could have done it from this expanded form, but didn't think of it. Or actually, I wanted to be able to pull out common factors anyhow. So the chain rule makes that a little bit easier. So here you can see the common factor of 32x. So this 16x squared times 2, pull out a 32x from that. And I can factor one of the x squared plus 1's out in front. So I'm taking one of these out with this one. So this one's gone. One of these is gone. That, let's go with the black, has been pulled out in front. Let's say the 16, and that 2x gives me the 32x. So I still have this x squared times 2 from the second part. So there's the negative 2x squared. From this first part, x squared plus 1. There's my x squared plus 1 all over that denominator. But now there's a common factor. We can cancel one of these with one of these. And here I have my simplified factored form for that first derivative. And I discover I have critical points when x is 0 and positive and negative 1. On to the second derivative. So in doing the second derivative, I didn't show it, but I took this 32x and I distributed it into the brackets here. So that here when I do low d high, I'm thinking of this 32x multiplied to the 1. The derivative of that is just 32. And this 32x times negative x squared gives me negative 32x cubed. Bring down the 3 times the 32, gives us the 96. Subtract 1 from the exponent. Then here again, I did it from, I kept it in factored form. So here's the high that'll be multiplied to d low. So 32x times 1 minus x squared. D low will bring down the 3, subtract 1 from the exponent. Inside doesn't change, times the derivative of the inside, which is 2x. And now we'll look at factoring this so we can find out when, for what values of x is this equal to 0. So again, there's a common factor of 32. So let's show a bit of the details here. So I'm factoring the 32 out from there, leaving a 1, and from there, leaving a 3. So that's where this 1 and this minus 3x squared come from. Then, this x squared minus 1, I should say x squared plus 1, and here I have an x squared plus 1. I have 2 of them there, 3 of them here, so I'm factoring out 2 of them. So that's why I have that exponent of 2 here. And then what I'm left with is one of these in the front. That's this one here. And in the back, I have factored out the 32, so it's gone. And I factored out all of this. So I have the 2x times 3 gives me the 6x times this x gives me the 6x squared times this 1 minus x squared in that bracket. Then we'll simplify what's inside that square bracket and at the same time cancel out here because this x squared plus 1 squared will reduce with the denominator to give me an exponent of 4 in the denominator. So there we go. When I simplify down this part inside the square bracket, I get this, which is not very pretty, but it's kind of like a quadratic because I could think of this as if I imagined that t was equal to x squared, then this would be t squared, so that's x squared squared, and this would be a t, so I have 3t squared minus 8t plus 1. So it's a quadratic. Is it factorable? Nope. Can I use the quadratic formula? Why, yes, I can. So that's what I'll do next. Using the quadratic formula to find out where is that numerator equal to 0. So I didn't actually use the t. I kept it as an x squared. So x squared is equal to negative b plus or minus square root of b squared. That's the negative 8 squared minus 4ac 12 all over 2a. And it doesn't give me a very nice number. Irrational numbers. So I'm going to go with decimal approximations because my goal here is to sketch a graph. And so the decimal value is going to make it easier for plotting the points. At this point, I did keep all the decimal places because here I do need to square root both sides still. So I figured out what x squared is, but I need to square root this, which means I square root this, take the positive negative, square root that, take the positive negative. So that's where these possible inflection points, that's where they're coming from. So 4 possible inflection points. And notice we said this was an even function. So I'm getting inflection points at the same value of x, positive or negative. Same value of x, positive or negative. And again, if we think up here for our critical points on the y-axis and then same value of x, positive, negative, we should have expected that because this is an even function. Well, there we go. We have 3 critical points, 4 possible inflection points. Let's put this stuff on a number line and see where that's going to lead us. So here's my number line. Now notice I just did the positive side. So I'm looking from 0 to the right because I know it's going to be mirrored on the left side. So I'm going to take advantage of the fact that it's an even function. So I have 2 of the critical points, 2 of the possible inflection points, and then I picked a test point out there to the right of the inflection point. And I figured out function values right away because I will want to plot both the x, y ordered pair. First derivative, 0 here, critical point, 0 there, critical point. Second derivative, 0 here, possible inflection point. So I do the second derivative test at each of these critical points. Discover here this will be a relative minimum. Here this will be a relative maximum. It's concave down, so this is an inflection point. Concavity changes where x is 0.4. And similarly, where x is 1.6, concavity is down at the left, up at the right. So I have an inflection point here at 1.6. So here we have four ordered pairs that I can plot on the right hand of my graph, and then use this concavity to help me sketch my curve. So you can still see it on your page, so that's good. Here's what happens when I plot these points. And that's what I'm getting. So near 0, 0.4, I don't remember what the y was. When x is 1, there's our critical point. We said this is a relative minimum. That's a relative maximum. Here's an inflection point. So it'll be concave down through this entire interval, concave up in this region over here. But first, let me mirror those points on the other side of the y-axis. And then we'll sketch the curve using the minimums, the maximums, and the inflection points. Concave up in this middle section, concave down up to the inflection point. I think that could be better. It looks like I've drawn it with the inflection point kind of up here. So I would lose some marks. Don't do this at home, kids. Be careful that it's concave down all the way to this point and then switches to concave up. It does need to be a smooth curve, so you don't want it to be concave down and then all of the sudden a weird edge angle corner kind of thing here. Still a smooth curve, but switching concavities at those points. There we go. That is 5.5, and this is a fairly complex function. So if that made sense to you, you are in good shape for practice. And that will take care of this lesson.